Hi all, welcome to the board plot problems discussion. So in this video we are going to do a problem based on the board plot. Okay, and we are going to draw the graph in semi-log graph sheet. And the problem is sketch the board plot for the following transfer function and determine the system gain k for the gain crossover frequency to be 5 radian per second. And our function is g of s equal to k square by 1 plus 0.2s into 1 plus 0.02s. So this is our function. So we have to sketch the board plot and we have to find the value of k corresponding to the gain crossover frequency 5. Okay, and one thing you have to notice that here for the gain crossover frequency means, so at that particular frequency the gain of our system, that is our magnitude of our system in decibel, will be 0. Okay, that's the point you have to note down. And if you are doing the board plot problems, the first step is to check whether the given function is in standard form. Okay, that is standard form means here the terms are given as the first order term, that is 1 plus 0.2s, 1 plus 0.02s, like that. Okay, so sometimes the questions may be like that, that is s square by s plus 3 into s plus 2, like that. G of s may be like that. Okay, so in that cases it is not in the standard form, that is it is s plus 3 and s plus 2. So we have to make it standard by taking outside the value 3 and 2. Okay, if you are taking outside the value 3, it becomes, that is 3 into s plus s by 3 plus 1, and if you are taking 2 from the second term, it becomes s by 2 plus 1. Okay, so likewise we have to make the term 1 plus st format. Okay, 1 plus st, if it is a first order form, we have to make it 1 plus st format. Okay, so that is a standard form, a first order function. Okay, and if it is a second order function, it's also we have to make it in a second order term, that is 1 plus, like that. So we will discuss it later. And this is the solution. So the first step is to write the sinusoidal transfer function g of j omega by substituting the value of s is equal to j omega. We will get the sinusoidal transfer function, and we are getting the function like that. And after that, just substitute k is equal to 1. Okay, initially we have to take the value of k as 1, and based on that value of k, we have to plot the board plot. Okay, so here we have taken the value of k is equal to 1, and g of j omega is obtained as like this. Okay, so in this term, in this function, we are having 3 terms. One term is j omega square, and another term is 1 by 1 plus j 0.2 omega, and another one is 1 by 1 plus j 0.02 omega. So 3 terms will be there. Okay, and we are going to do the magnitude calculate we are going to do the calculations of for magnitude plot first. Okay, so for that, first we have to find the corner frequencies. So from the current knowledge, we understood that the corner frequency will be there for first order and second order systems. Okay, that is corner frequency is nothing but it is the joining of two asymptotes. Okay, that is it's a slight change. If you are drawing the magnitude plot, then there will be a slope change at a particular frequency. Okay, the frequency corresponding to that slope change is corner frequency omega c. Okay, that is if it is a 0 decibel per decade line, and at a particular frequency omega c, it becomes minus 20 decibel per decade. Okay, slope becomes minus 20 per decibel per decade. So at that particular frequency is called the corner frequency. So here, for finding the corner frequency, we have to find the reciprocal of the j omega term. Okay, the corner frequency will be there only for here the first order terms are there. So corner frequency will be there for these first order terms. Okay, so the first reciprocal of j omega, sorry, the coefficient of j omega is 0.2. So reciprocal of 0.2 is 1 by 0.2, it is 5, and another one is 1 by 0.02, that is 50. Okay, so we have to denote the corner frequencies in the increasing manner, that is omega c1 is taken as 5 and omega c2 is taken as 50. Okay, and after that we have to draw a table having 4 columns: time, corner frequency, slope, and change in slope. Okay, and in the first column we have to write the terms. I have already said that there are 3 terms for a function, that is j omega square, and another one is 1 by 1 plus j 0.2 omega and 1 by 1 plus j 0.02 omega. So we have to write these terms in an order such that in the increasing order of the corner frequency. Okay, so we know that the j omega square term, okay, j omega square term will not have a corner frequency. Okay, so it is written first, and after that we know that the corner frequency is 5 and 50 for the 2 terms. So we have to first write the term which have the corner frequency as 5 radian per second. So it is this 1 by 1 plus j 0.2 omega. So we have just write the term, and third term is 1 by 1 plus j 0.02 omega. Its corner frequency is 50, so increasing order of corner frequency. And after that we have to write the slope. As we know, the j omega square term is in the numerator and its power is 2, so the slope will be plus 40. Okay, and here the j omega term is in the denominator. Okay, the for the 2 terms the j omega term is in the denominator, so the slope will be minus 20 and minus 20. Okay, and the concept is that if the j omega term is in the numerator, the slope will be plus 20. If j omega square is in the numerator, it will be plus 40. If j omega cube in the numerator, it will become plus 60. Okay, so likewise we can write the slope, and after that we have to write the change in slope. So change in slope can be found by adding the first change in slope can be found by adding these 2 terms. Okay, whatever may be the question, the procedure is same. Okay, we have to add the first 2 terms, that is 40 minus 20, we will get it as 20. Okay, and after that we have to add this 20 with the slope minus 20. Okay, that is crosswise we have to add, so 20 minus 20 becomes 0. Okay, so actually this change in slope means if we are drawing our magnitude plot, okay, if we are drawing our magnitude plot, our slope, normally our graph will be, that is the slope will be starting for this j omega square. We know that the slope is plus 40. Okay, that is like this, plus 40. Okay, and at the first corner frequency 5 we are adding a term 1 by 1 plus j 0.2 omega, which have a slope of minus 20. Okay, so at this 5 radian per second, we are adding a term having minus 20, so the slope will reduce to 20. That is, already to have 40 decibel per decade slope. Okay, if you are adding a minus 20, the slope will become 20. Okay, and at 50 radian per second we are adding another term, and it is also having minus 20, so the slope becomes 0. Okay, so at this particular, this is omega c1 and this one is omega c2. Okay, and approximately our graph shape will be like that. Okay, so 2 changes will be there. So actually that is the concept of this magnitude plot. Okay, and next step is to find a lower and higher frequency omega L and omega H. So omega L is chosen less than the value of omega c1. Okay, so omega c1 is 5 we know, so omega L is chosen as 0.5 radian per second. Okay, that is, we have to choose a much less value than omega c1. That's all. There is not a particular rule for selecting that omega L and omega H. Okay, and we have to choose that omega H as higher than the omega c2. Okay, omega H is higher than the omega c2. That is, omega c2 we know that it is 50, omega c2 is 50, so omega H is chosen as 100. Okay, so we have 4 frequencies: 0.5, then 5, 50 and 100. Okay, and we have to find the corresponding gain in decibel for these 4 frequencies. Okay, so first we are going to find the gain at omega is equal to omega L, that is omega is equal to 0.5 radian per second, and gain equation is 20 log mod j omega square. That is, inside this mod we have to write the first term in our table, that is j omega square. Okay, so we know that 20 log mod j omega square means it is 20 log omega square. Okay, when this term j omega square comes out of that modulus, it becomes omega square only, and we have to substitute omega 0.5, and we will get the value as minus 12 decibel. It is the magnitude corresponding to omega L, and at omega equal to omega c1, the equation is same, 20 log j omega square, and we will get the value as 28 decibel. Okay, so whatever may be the question, whatever may be the function, the first two equation corresponding to two frequencies, that is omega L and omega c1, is same. Okay, that is the only difference is will be in its the value inside this modulus. Okay, so always keep in mind that is we have to write the value. Okay, write the first term in our table. Okay, that is j omega square. That is, we can say that except the first order and second order terms, whatever may be the another values or terms left in our function, we have to write that inside this modulus value. Okay, mod value. And for finding the gain at omega equal to omega c2, the equation is a is equal to slope from omega c1 to omega c2 into log omega c2 by omega c1 plus gain at omega equal to omega c1. That is, we have to add the gain at the previous frequency, that is omega c1. The previous frequency is 28, so we have to add that 28 with this value. So the slope from omega c1 to omega c2, actually that is this first term, that is 20, change in slope. That is, if you are drawing the approximate graph in the previous slide, we have found that this is the approximate graph. This is omega c1 and omega c2, this one. So slope from omega, this is 40, this is 20, and this is 0. So slope from omega c1 to omega c2, okay, slope from omega c1 to omega c2 is 20. So actually that is calculated here. Okay, so instead of the first term here, okay, instead of this first term, that is slope from omega c1 to omega c2, we have to write this 20, okay, into log omega c2 by omega c1 plus gain at omega is equal to omega c1, that is 28. So 20 log 50 by 5 plus 28, and we will get the answer as 48 decibel. And for finding the gain at omega equal to omega h, equation is slope from omega c2 to omega h. Okay, slope from omega c2 to omega h into log omega h by omega c2 plus gain at omega equal to omega c2. Okay, and the slope from omega c2 to omega h is 0. Okay, that is second term in the change in slope column. That is 0 into log 100 by 50 plus 48, that is gain at the previous frequency. Okay, so these are the 4 points, that is 4 gains corresponding to 4 frequencies. Okay, and next we are going to calculate the values for phase plot, and for that we have to write the phase angle. Okay, phase angle. So this is our function, and we know that phase angle can be write phi equal to, first you have to write the angle of the numerator part. Numerator is j omega square. Okay, numerator is j omega square, so we know that the angle is plus 180. If it is only a j omega in numerator, it becomes plus 90. If it is j omega cube in numerator, it becomes plus 270. Okay, and after that we have to calculate the angle in the denominator, so it will be a negative angle, and we know that equation of angle will be tan inverse b by a, that is tan inverse b by a means tan inverse 0.2 omega by 1. Okay, that is, which means 0.2 omega. Okay, and minus tan inverse 0.02 omega. Okay, 0.2 omega. So that is the actual equation that you can see here. 180 minus tan inverse 0.2 omega minus tan inverse 0.02 omega. Okay, and we have to choose certain values for, okay, some random values for this omega, that is in between the omega L and omega h. Omega L is 0.5 and omega h is 100. So in between these omega L and omega h, we have to choose some values. Okay, so for that frequencies we have to find the phi. Okay, so here you can see they have calculated the terms, that is tan inverse 0.2 omega and tan inverse 0.02 omega. Okay, and after that they are calculating the phi. So if you are calculating the if you are using the calculator, okay, we can directly type this equation, and we can substitute the value of omega for different values. Okay, and these are the corresponding 5 for different values of omega. Okay, so that's all about the calculations, and after that we have to draw the graph. Okay, so this is the graph, actual graph, and here this will be the magnitude plot, and this will be the phase plot. Always in the semi-log graph sheet, the top portion, in the top portion we will be drawing the magnitude plot, and in the lower portion we will be drawing the phase plot. Okay, and we know that the magnitude plot, the axis are omega. Okay, that is actually it is log omega, but we are drawing that in the logarithmic scale. Okay, so we are here to take the value omega here in the x-axis, and the y-axis it is gain in decibel, that is a in decibel, gain in decibel, magnitude in decibel. Okay, and we know that the omega L is 0.5 and omega H is 100. Okay, so the lowest value is 0.5 and highest value is 100, so we have to accommodate that values in this graph. Okay, so we are starting from 0.1, that is much lesser value than 0.5. So first line is 0.1. Okay, and we know that the next line corresponding to this 2, it will be 0.2, then corresponding to 3 it will be 0.3, and like that. If the next one comes here, okay, in the board plot, in the semi-log graph sheet, you can see 1 2 3 4 5 6 up to 9, and again 1 2 3 4 up 6 up to 9, like that. Okay, so for each one, okay, when each one comes, it means the frequency is multiplying by 10. Okay, so the first frequencies we are choosing it as 0.1, and for the next one it will become 0.1 into 10, that is 1 radian per second, and for the next one it become 10 radian per second, for the next one it become 100 radian per second. So like that we have to mark. And in the y-axis, and we know that the maximum and minimum values are, it is -12 and 48. Okay, so we have to choose a maximum value for 50 decibel, and -10 is lowest. Okay, so likewise we can select the scale here. The topmost line is 50, and the next dark line is 40, then 30, 20, 10, 0, then -10, -20. Okay, up to -20 we have to choose, because we have to mark the point -12 and 48. Okay, so that points we can accommodate in between this -20 up to 50 range. Okay, so after that we have to mark the 4 points. So the first point is, that is omega L, that is corresponding to 0.5. the decibel magnitude is -12, that is 0.5. you can see here, that is this is 0.1, and this is 0.2, so 5 comes here. Okay, this is 0.5. Okay, and -12 approximately we can take that -12 from here. So here you can put a cross mark or any mark. Okay, so this is the first point, and likewise for the next frequency 5, we are getting the magnitude as 28, so this is the second point, and this is the third point. Okay, and this is the fourth point. So likewise we have to mark the points. Okay, and after that we have to connect that points. Okay, we have to connect that points using the scale. Okay, straight lines you can draw. So this is the magnitude plot corresponding to the value k is equal to 1. Okay, you have to write the value k is equal to 1 here. Okay, k is equal to 1, and after that we have to plot the this phase plot. Okay, phase plot. So for each frequency we are having different angles. So here the maximum and minimum value is 174 to 30. Okay, 174 to 30. So in the graph we are choosing the lowest value is 20. Okay, 20, 30, 40, 50, 60 up to 180. Okay, up to 180, because we have to accommodate these values, that is 30 to 174. So we are taking 20 to 180 only. Okay, so based on the frequencies and 5, we have to choose some points. Okay, we can mark some points. After that, just draw the graph by freehand. Don't use scale. Okay, so the line will be a curved line. Okay, that is actually we have to draw by freehand. Okay, so we will get the phase plot like this. So we are having a magnitude plot here and a phase plot here. Okay, so that's about the sketching of the board plot. But in the question, they have asked that we have to find the value of k, system gain k, for the gain crossover frequency to be 5 radian per second. Okay, we know that gain crossover frequency means at the gain crossover frequency our decibel magnitude will be 0. Okay, that is if the 0.5, that is 5 radian per second. Okay, if the 5 radian per second is to be a phase crossover frequency, okay, sorry, gain crossover frequency, that is this gain crossover frequency, that is 5. Okay, so if the value 5 is that is 5 radian, 5 means 5 radian per second, that is 5 radian per second. Okay, that is if this 5 is corresponding to the gain crossover frequency, that is if this 5 is a gain crossover frequency, then the corresponding magnitude, okay, then the corresponding magnitude should be 0 decibel. Okay, so if you are observing our graph corresponding to this value, that is 5, in our actual graph the decibel magnitude is approximately 28. Okay, it is not 0, it is 28. So for the gain crossover frequency 5, okay, 5 to be a gain crossover frequency, the corresponding magnitude, okay, magnitude value will be 0. Okay, that is 0. So we have to choose a point. Okay, we have to choose a point 28 less than our previous value. Okay, that is actually we are drawing another graph, okay, with a less magnitude, that is less magnitude means 28 less compared to our previous graph, that is previous graph corresponding to k is equal to 1. Okay, because at 5 radian per second the magnitude value is 28. Okay, so for this 5 to be the gain crossover frequency, the value of magnitude should be 0, but here it is 28. Okay, so we have to decrease the gain by 28. Okay, so we have to plot another magnitude plot. We have to plot another magnitude plot, that is we have to reduce each point, that is we are having 4 points. Okay, that is one at 0.5, one at 5, and another at 50, and another at 100. Okay, so for all these points we have to reduce the gain value by 28. Okay, and we have to plot 4 points, and after that we have to draw the line. Okay, so this is the actual magnitude plot we have to obtain. Okay, so the first one is the magnitude plot corresponding to the k is equal to 1. Okay, but we are asked to find the corresponding k corresponding to the gain crossover frequency 5. Okay, and here you can read that given that the gain crossover frequency is 5 radian per second, at omega is equal to 5 radian per second, the gain is 28 decibel. Okay, so if gain crossover frequency is 5 radian per second, then at that frequency the decibel gain should be 0. Hence to every point of magnitude plot a decibel gain of minus 28 decibel should be added, that is we are reducing the gain by 28, that is minus 28. Okay, the addition of minus 28 decibel shift the plot downwards. Okay, the plot comes downwards. The corrected magnitude plot is obtained by shifting the plot with k is equal to 1 by 28 decibel downward. Okay, the magnitude correction is independent of frequency, so we have to write the equation as 20 log k is equal to minus 28 decibel, that is we have reduced the value by 28 decibel here. So 20 log k will be equal to minus 28, and from that the value of k will be obtained, it is 0.0392. Okay, and you have to just write the k value of k, okay, corresponding to this graph, that is this plot, k is equal to 0. What is that value? 0.0398. Okay, so that is the final figure. So here we have just drawn the magnitude plot corresponding to k is equal to 1. Okay, and then after that we have drawn the phase plot. Okay, then we have to make the necessary correction as per our question. Okay, so after that we have to again draw the magnitude plot, that is the corrected magnitude plot. Okay, so that's the actual procedure here. I hope all of you understand the problem well, and thank you.